one.
Welcome to Creative Escape, sponsored by the Center for Research on Teaching and Learning Excellence. I'm Dr. Ann Cavallo. I'm Assistant Vice Provost and Director of the Center, and I'm here with Dr. Andrew Clark, who's Associate Director. Today's topic is Astronomy and Space Exploration with Dr. Neela Virabathina and Dr. Ramon Lopez, both of the Department of Physics, College of Science. First to welcome us today is Interim Provost, Dr. Pranesh Aswat.
Thank you, Dr. Ann Cavallo, for the introduction, and thank you both, you and Dr. Andrew Clark from the Center for Research on Teaching and Learning Excellence for organizing the Creative Escape series. I know we started this last year during the midst of the pandemic, and it was an exciting opportunity for UTA faculty, staff, and students and the broader community to come together and learn about new and exciting things that were going on at UTA, and also an opportunity for us to hear from our faculty who are doing some really very interesting things and talking about topics that were of general interest for a broader community and across both within the university as well as the broader community in the greater Arlington area. As the situation with COVID improves, I think still having these presentations and showcasing our faculty is an important part of an outreach activity that we have to both the faculty across campus and staff on campus and our community in Arlington. So this summer, every 2 weeks, we are going to have different faculty from different parts of campus come and talk about some interesting topics. Today we have a topic which is very close to my heart as well, with two outstanding faculty from the Department of Physics, Dr. Neela Virabathina and Dr. Ramon Lopez. So we're going to talk about topics within the area of astronomy and space exploration. So please join me in welcoming both of them here today. And again, a big round of applause for Anne and Andrew for organizing this series. We have 5 of them through this summer, so I hope you all enjoy the conversation as much as I'm looking forward to them as well. With that, I'm going to turn it over to Neela for the first presentation.
Thank you, Dr. Aswat. We'll do the little agenda first and then go from there. And so here we have, as Dr. Aswat said, first faculty presentation is Neela, Dr. Virabathina, on celestial beauty, spot and shoot. And then Dr. Ramon Lopez will speak on electric space. We will have then questions and discussion, and then contact us for the next event and information on the next event after that. So do put your questions in. There's a place to put all your questions, and we will address them after our presentations. And now we'll turn it over to Neela. Thanks.
Thank you, everyone. Am I audible?
Yes, you are.
Great. So I'm going to share my screen. Here we go. It's my pleasure to today to be a presenter in the inaugural session of Creative Escapes series for this year. The title Creative Escapes inspired me, and so much so that I jot down some lines. And let me read those to you. I hope it comes up. In the hustle bustle of life, hectic schedules and daily routine, we forget to enjoy the nature, calmness, and serenity. Let's escape into the celestial splendor and beauty to adore the stars, suns, and universe creativity. Think how many of you actually go out and scan the sky and space and your natural surroundings. We just get so busy with all other things. In that regard, students are not unusual. Same thing happens with them when they join the courses. They get so engrossed in the technicalities of the courses, assignments, tests, anxiety, the social pressure, personal problems. So I started to give them this project that's I named Celestial Beauty Spot and Shoot. And the timings, like during the lockdown and pandemic, online learning, I thought, why should I not continue this project? And even though we are not meeting face to face, students are online. This is something they can do it from anywhere in the world. Doesn't matter wherever they are. They can involve their friends. They can involve their family, so they can make some kind of social connection. So I continued doing this project. I encourage them to observe the sky and follow the objects. I gave them the list. For that, they do not need any special equipment. All they need to do is just go outside and observe. If they have their binoculars, telescopes, cameras, they can use like fancy cameras. Otherwise, just the regular cell phones. So I teach to hundreds of students. Today, I'm going to share some of the selected images that my students have taken. This one over here, one of my students was coming back from the Arkansas to Texas. On the way, just stopped in New Boston area to grab a cup of coffee, and it was dark sky. Observed this band of Milky Way going across. I happened to had a SLR camera with him. Just took the camera out, did not have tripod, so somehow fixed the camera on the top of his car and shot this image. It's a beautiful image, and here you can also see Jupiter. This one is the pictures taken just with the regular cell phone. Behind the building, you get to see moon. In the cell phone, the moon will not come big, and that's okay. That's what I tell my student, doesn't matter. Just follow it and get pictures regularly, every other day, every 2 days, every 3 days. And at the end of the semester, of course, they have to submit all the images with their report. Okay. So this is the moon here, and the other bright object you see is Venus. Okay. The students at the same time also shot this, where you get to see 3 belt stars of the Orion constellation. This one here, students explained she had a telescope that was just sitting in the closet for probably number of years. Because of this project, she and her family took the telescope out, they cleaned the telescope, and then started to shoot these images. As you can see here on the left side, the image of the moon, and one of the images, of course, the student took lots of images. Okay. Another student who was not in the DFW at the time of the lockdown, he was in another city, happened to own a telescope, so took the telescope out, started to take pictures of Venus and moon together. That was last year. Also used an app, so you will see the images where the student is making comparison how the objects look in one of the apps and how they look in the sky. App gives you a little bit more details. Here you can see moon and Venus, and here you can see moon and Venus in the real sky. This is just using the regular cell phone. Here is the picture from another student. You can see number of objects behind the house of the student. And here when we zoom in actually, with Venus and Moon, you also start to see Pleiades cluster, which are the 7 stars or small group of stars that we also have the same logo on Subaru car if anybody owns that. Okay. Some of the students, instead of taking the pictures, they decided to draw it, and I told them that's perfectly fine as long as they can try to draw it pretty much to scale, especially with respect to a building, and they follow those objects with respect to the same object and also with respect to each other. So here you can see the drawings of these objects and how the distance between those objects changed over the period of time. And some of the students even did much simpler work. However, they used a stick to scale those objects. So they hold the stick on the hand distance, and then they saw where are these objects in the sky and followed them for a few semesters. Sorry, not semester, for a few weeks over the semester. Here are some more. One of the students during the lockdown, international student, was staying in Japan at that time and did not know what to do. And he figured out there is a water body, a lake near the home. He just took his camera, went near the lake, started to take the pictures of the moon, as you can see over here. Beautiful picture with the mountains, sky, water, and the moon. Here we go. Here is just using the regular cell phone, the entire Orion constellation you can see over DFW area. Some of the students followed the sunset or the sunrise over a few weeks to see how its location changes in the sky. Actually, some of the students also made the time-lapse videos. For the time constants, I just put the pictures here, not the videos. And we get to see these were taken near the Mountain View College in Dallas. And here, atmospheric phenomena. I always tell my students you don't have to observe like only the objects in the sky. How about the clouds, our own atmosphere? So here you can see a halo around the moon. Most important is when the students turn in their reports and the pictures at the end of the semester, I also ask them to write their reflection, their experiences. So here's some of the reflections as you can read. I never knew the sunsets are this beautiful. I would always see pictures posted by people, but never really did it myself. Now I'm so amazed by it that I go outside every day just to look at the sunset. Okay, and somebody said, my kids and I now enjoy predicting the phase of the moon, and then we follow it every day. And this one over here, this experience was so calming that when I feel sad and depressed, I just go outside and start looking at different things. I start to feel connected. So that connection with the universe, I think that's what the students learn. We are the part of the universe and universe is part of us. So now the question is, I hope you are inspired by these images taken by students. If you want to do so, here I would like to share some tips with you. So if you want to observe the moon, and nowadays beautiful crescent moon, I am observing it since last 3 or 4 days myself. And the best tip I can give you is look what side of the moon is lit. If it's lit on the right side, that is a waxing cycle. It means a growing cycle. The next day you will see it becoming bigger and bigger, more and more illuminated part. If it's lit on the left side, you know it's a waning cycle. It's a shrinking cycle. You will see it more less and less of the illuminated part. So that's how you can start predicting the phases and see if you really get what you are predicting the next day, and also the motion of the moon across the sky. In what direction is it showing? Eastward motion or westward motion? Again, I would encourage, if you want to do it, involve the friends, involve the family. Okay? This is a fun activity to do it together. Planets during June and July this year, we have Venus and Mars in the evening sky after the sunset until about 10 or 11 in the evening. By the mid-July, July 12th or 13th, Venus and Mars will be very close to each other in the sky, and moon will be closer to them too. That will be a wonderful opportunity to capture these three objects together. Jupiter and Saturn, they are visible in the morning sky after they are rising, like after 1 a.m. However, starting from next week, Jupiter will be visible like after like 11 p.m. in the night until morning. So you can capture them in the night time. Mercury is usually hard to capture without the telescopes because it stays pretty close to the sun and close to the horizon too. Stars and constellations, just get yourself familiar, find 1 or 2 constellations in the sky and hop to the other constellations from them. Okay. If you want to observe sunset or sunrise, if you want to take pictures, observe them from the same location against a fixed object, a tree or pole or something. Only then you can figure out how the sun is moving across the sky, across the horizon. In the summer, you will see it moving from east to north, and in the winter from east to south. Okay. Band of Milky Way, well, go in the countryside, go outside the light pollution area. Dallas Fort Worth, you won't see it from here. Okay. Zodiacal lights, these are very faint, diffused light spread by the dust particles in our own solar system, interplanetary dust, like triangular shape. Again, from DFW, probably you will not see it. However, if you go outside the DFW area, you might see it right after the sunset or right before the sunrise. Okay. Clouds, sky, sun, they all make this atmospheric phenomena so beautiful. Halos, the noctilucent clouds, are clouds that shine in the night. Sometimes the rays pass through the clouds. So all of these different phenomena can be captured. You can go to this website of NASA. You can sign up to get the notification when the International Space Station is going over your area, and you can follow for 5 minutes or 6 minutes. It's very nice, just especially for kids, to show them the International Space Station looks like just like a star moving across, or just like a tiny airplane moving across. You don't have, if you do not know how to locate these objects, well, with the advantage of technology, now things are much easier. Just like on our phones, we use GPS to go like Google Map or other maps to go around. Same thing, there are many free apps such as Google Sky, Stellarium, and many others. Some of them I have named here. You can download them. All you have to do is just hold it in your hand, put it up your head, and it will show you what objects are there in the sky. Or if you want to find something special, just put the name of that object. It will take you there. Just like we do it in Google Map. We put the address, it takes us there. These apps work in a similar way. Okay. Now, when you are taking these pictures, when you are using your cameras, cell phone cameras, or if you want to use more fancy cameras to get better pictures, maybe you want to publish them. There are actually many websites, for example, Astronomy Picture of the Day, the World at Night, the Capture the Dark, and the Space Weather, where they accept the pictures from the public. Anybody can submit the images to these websites. There are images from professional astronomers, also from professional telescopes, ground and space-based telescopes, and also from anyone who wants to submit their own pictures. I do not know how I'm doing as far as the time goes. If it allows me, I will show you these websites shortly, but first let me finish a couple of other slides. Okay. If you want to take one step further, okay, not only just going out and observing the sky, taking the photographs, astronomy is unique in that sense. Okay. There have been many discoveries and scientific contribution made by amateur astronomers, people who just have hobby. They can make actual contribution to science, to research. Okay? And there are many projects that depend on contribution from everyone. Here is some of the list I put, like Galaxy Zoo or Zooniverse, where you can go online and help the astronomers or submit your own data. So there are different ways to be involved in these scientific projects. I usually give a separate talk on this topic, but for now I just put it here. I hope you all are inspired, and in this summer you will go out and you will enjoy the surroundings, and you will enjoy the sky around you. So let me quickly share with you. Here is the Astronomy Picture of the Day website. That's the picture they posted today. You can see the Scorpius constellation against the background, or you can go over here and it gives you the archive of pictures taken from around the world for last 15 or 20 years. Okay. Here is the spaceweather.com. You will also hear about this website probably in the next presentation. Here, lots of images of everyday pictures of real-time aurora photo galleries, real-time space weather, real-time clouds. Okay. So all those images, hundreds and hundreds of those images you will get over there. Okay. And again, keeping the time in my mind, I should not go more over these sites. I will just end up with one of the poems that actually one of my students wrote. Okay, so I'm just quickly going to read it for you. In my first semester of university, the pandemic did not stop anyone from viewing the night sky, watching the planets and learning their names and what those names hold within. To me, the online world isn't a wall holding me back. from learning about the world, astronomy is no different. I can write from anywhere, I can read from anywhere, I can see the world from anywhere. So basically the student is saying you can enjoy the world from anywhere, pandemic or no pandemic, online or no online. Okay? So with this, I would like to thank all of you, and so keep enjoying the inner and the outer beauty. Okay? Feel connected with the universe.
Thank you so much. We'll now have Ramon Lopez start his talk. Thank you.
I will go ahead and stop sharing my slides.
Yes. Yep.
Okay, now I'm unmuted and I can start sharing. Oh, I think, yes, we discovered that what I have to do is actually share the screen. So do you see it, Anne? Do you see the title?
We do.
Yes.
Good. All right. So my name is Ramon Lopez. I'm professor of physics in the Department of Physics here at UTA. I'm a space scientist primarily. I also work a lot in physics education, and I'm one of the co-directors of the UTeach program, working along with Ann Cavallo and Greg Hale from the College of Science on that. Now, since I am a physicist, I like physics, and I think people should know a little bit of physics, especially about things that affect them. And I'd like to give you a depiction of the consequences of not understanding physics. So I'm not going to say any more at this point. I'm just going to go through the slides and you can see what can happen if you don't understand physics. So the lesson is, don't let that happen to you. Know the physics of a situation. So now I want to come to my topic, space, electric space. You'll soon see why I chose that phrase, electric space. So what I'd like you to do is just spend, 10, 15 seconds thinking, well, what words come to mind when you hear the word space, like in outer space, and just type it into the chat. There's the Q&A chat, and just type in a word, and just do that in the next very short period of time. And let's see what word comes to mind to all of you when you think of space. And I should be able to see the Q&A, yeah? Show Q&A, okay. So, I'm not seeing, okay, here's some new ones. Okay, room, empty. Oh, they're going to published, okay. Medium for everything, infinite mass, vast, open, stars, unlimited. We've got 9. Let's see if we can get it up to about 20 or so before I go on. Forces, any other, just a word that comes to mind. Okay, so we've got 16 things here. And so I think I see stars, planets, nebula. Somebody else said stars, open, room, empty. Those are the kinds of things that actually, if you just ask somebody, what's space? And they'll say things like that. Oh, it's empty. In space, nobody can hear you scream, that sort of thing. And you think of stars and planets and room. Well, yes, all those things are there. But there's also much, much more. And that's why I titled this talk Electric Space. Actually, Electric Space is the name of a museum exhibit on this particular topic that I worked on with a colleague back in the 90s. It was a 4,000 square foot museum exhibit that toured science museums in the US. I don't think it ever came to Dallas-Fort Worth, though. But actually, the message that we tried to convey in that exhibit, and that I'm going to convey to you now, is that space is not empty. It's filled with electrically charged particles, what we call a plasma, the fourth state of matter, and with magnetic fields and electricity and electric currents. Space is electric in a real sense. And that's really the structure of space, is magnetic fields of different objects and electric currents separating those regions of magnetic field and plasmas flowing through, and the electromagnetic forces acting on all of these things. Our space really is electric space. And the story for this really begins with the sun. And here you see the sun in white light, picture taken from the ground. Sunspots are occasionally visible, like right here. You see a couple of sunspots coming around the surface of the sun. And those sunspots and the variation in the sunspots, which is in the chart down below showing the solar cycle, the number of sunspots goes up and down roughly every 11 years. That's an indication of the magnetic behavior of the sun. And what happens in the sun happens in other stars as well. Stars have magnetic fields and they have magnetic activity cycles, and that magnetic field is very critical to the dynamics of stars. And here you see a couple of examples. You see a solar flare going off on the right-hand side. This picture is actually taken in X-rays. So this is of very high energy particles and regions of plasma, the electrically conducting gas that the sun is made of, that are reaching, millions of degrees, because only something that's that hot, that's a million plus degrees, is actually going to radiate in X-rays. And you see those loops of magnetic field essentially outlined by the hot plasma. And then here on the left-hand side, we see on the edge of the sun an erupting prominence. This is in extreme ultraviolet, so close to X-rays, but you see this enormous cloud of material lifting off and blowing off the surface of the sun, and some of that material falling back down. Our sun is boiling and churning all of the time, and the magnetic field is critical for those kinds of dynamics. And if you think about it, magnetic fields are actually much stronger than gravity. You saw that we still have the picture on the right-hand side of this loop being held up against the sun's gravity. And on the left, you saw this cloud blowing off from the sun. Well, that's blowing off against the sun's gravity. The sun's gravity is pulling stuff down. But all of you probably have got little refrigerator magnets. I certainly do. They might be holding up a family picture or this week's shopping list. But consider the fact that that little magnet is holding up a piece of paper and keeping it from falling. Meanwhile, the entire mass of Earth is pulling on that paper with gravity. And the force of that tiny magnet is greater than the force of gravity being exerted by the entire mass of our planet. So magnetic fields are really quite strong. And that's why the magnetic field of the sun plays such an important role in the atmosphere and the dynamics of the atmosphere of the sun. And you can see this actually also during eclipses. This is a picture taken from the Great American Eclipse of 2017 that crossed over the continental United States from the Pacific Northwest down to the middle and then exiting in South Carolina. And you all know that we are going to have a total solar eclipse come overhead us on April 8th, 2024. There'll be a total solar eclipse that'll sweep up through Texas and up through the Midwest and then exit, the shadow will exit over Canada into the Atlantic Ocean. So that's going to be a very exciting event because the path of totality will pass over UT Arlington. But when you have a total solar eclipse, you can see that outer atmosphere of the sun that normally you can't see. And you can see that the corona, the atmosphere of the sun, is 1 million to 2 million degrees in temperature, which is very difficult to understand given the surface temperature of the sun is 6,000 degrees. But what's transferring the energy from the sun, it's not heat that's transferring energy, it is the magnetic field and waves in the magnetic field and twists and turns in the magnetic field that's tied to the boiling and churning plasma in the upper layers of the sun. So all that boiling and churning twists up the magnetic field, and those twists are stored energy that some of it is just generally released to heat up the atmosphere of the sun. Some of it gets stored into big, big twists and is suddenly released, as in those videos that you saw before. And we can get solar flares and what are called coronal mass ejections coming out from the sun. But because the sun's atmosphere is so hot, because of the role that the magnetic field plays in the dynamics, it's so hot sun's gravity can't hold it down. And the pressure of the atmosphere pushes out, accelerating the atmosphere of the sun until it goes supersonic and flows out, filling all of the space between the planets with what we call the solar wind. And the solar wind drags the sun's magnetic field with it. The sun's magnetic field is tied to the plasma of the solar wind because the plasma is essentially infinitely conducting, and so the magnetic field can't let loose of the plasma and it's dragged out. So our space, our solar system, is filled with the outer atmosphere of the sun and the magnetic field of the sun pulled by that solar wind. And when that solar wind interacts with the Earth, it hits the Earth's magnetic field, which is shaped like a dipole, the kind of shape you get if you put a bar magnet on a piece of paper and sprinkle some iron filings. You get this dipole magnetic field. I'll replay this video. This is not just, it's not a cartoon. This is actually an initialization run from a simulation. So the solar wind flows past the Earth's dipole and it squeezes Earth's magnetic field on the side facing the sun and stretches it into a tail on the night side of the Earth. And this is not the size of the Earth, by the way. This is 3.5 times the size of the Earth. So this magnetosphere is a large comet-shaped region controlled by the Earth's magnetic field. And the shape is like a comet for the same reason that a comet is shaped like a comet. The solar wind is blowing past it and pulling out this tail. And what that really means is that there are electric currents that are flowing that are distorting the magnetic field, creating that shape. Some of those currents flow in and out of the upper atmosphere of the Earth as drawn in this artist diagram. And then they light up the sky. These pictures were taken in Alaska, Fairbanks, Alaska. And when those electric currents are strong enough, they light up the sky in the same way that an electric current through a neon tube, and you might be sitting in a room where you've got fluorescent lights. It's more or less the same kind of process that creates those lights. But we call it the aurora, the northern lights. And this is what it looks like seen in space. The bottom part of the aurora, this sort of lower level, that's at about 110 kilometers in height. And the aurora forms a couple of big circles around the magnetic poles because it is related to the magnetism of the Earth, not to its rotation. And there's also aurora in the southern hemisphere. They are linked to each other, in fact. So they both form these big circles. Now, we've known about this kind of stuff for a long time, actually, because in the early days of worldwide navigation, people started to notice that, well, they noticed right away, actually, once they were crossing the Atlantic, that the compass needle changed direction relative to true north. And that's because the North Pole magnetic is not in the same place as the geographic pole. So as you move either east or west, the angle between the two changes. And so there was an attempt to map that and to so that a navigator could correct the compass reading depending on where they were. But that kind of study discovered that sometimes the compass needles would sort of wiggle on their own, and nobody understood what that could be. But in the 19th century, Alexander von Humboldt set up magnetic observatories throughout the world as he was exploring it. And Gauss and Humboldt worked together on what Gauss called the magnetic campaign to study Earth's magnetic field, which was very mysterious. And they showed that these magnetic storms, these irregular variations in Earth's magnetism, were global, and they would just happen. And nobody understood what could be affecting the whole magnetic field of the Earth. Well, all of this might be very interesting, but why should we really care? Well, we care because our technology is based on electromagnetism, and these magnetic changes in Earth's magnetic field, the currents that are flowing through the Earth's ionosphere to make the aurora, all of this has an effect on our technology. And these things are linked to other phenomena out in space, such as increased levels of high energy radiation that can damage spacecraft. So all of that, the changes in the space environment that can affect our technology, that's called space weather. So as I said, you've got high energy particles in space that can damage satellites. They can damage astronauts as well. Astronaut safety is a very important thing, and radiation can be very, very nasty. The currents flowing through the ionosphere generate electric currents that can cause disturbances in the ionosphere, making it impossible to communicate by radio. And that can have a significant impact on GPS. And GPS is used for many, many things. People don't realize how tied our economy is to GPS. So being able to predict when you're going to lose GPS is actually very important. These changing currents in the ionosphere also induce electric currents in nearby conductors, and big nearby conductors are things that humans have built. In fact, that's how we first ran into space weather, was when we started building things that could act as natural antennas and that could be affected by these ionospheric currents and the currents that they would induce in nearby conductors. So that can affect our power grid. It can cause pipelines to corrode. There's all kinds of effects there. So there are many, many effects of space weather. Now, the sun can surprise us at any time, and in late October of 2003, it did that with what we call the Halloween storms. Here we see the sun again in white light, a few sunspots, but then by early October, there wasn't very much at all. And then suddenly one, and then a second one, and then a third one just erupted out of the sun right in front of us. And these enormous, enormous regions of concentrated magnetic field, these sunspots, started blowing off one explosion after another, sending clouds of plasma and magnetic field hurtling through interplanetary space, some of which hit Earth. And here you see one of the big solar flares going off from this big region down here. And we're going to zoom out and see other explosions that came off from the sun as recorded in a series of telescopes. All that white fuzz you see in the image, those are high energy particles hitting the camera, which is on a spacecraft about 1 million miles from the Earth, between the Earth and the sun, and it monitors the sun. And there were, so this is what the sun threw at us over a period of several days, these big explosions, and that actually shut down many systems in spacecraft, including this one. And there were lots of effects. I mean, there were things like aurora seen in Texas and on the border between Florida and Georgia and in other unexpected places. There were some technology damage. There were a couple of Japanese communication satellites that were damaged, and one was never recovered. Lots and lots of satellite anomalies. There was a spacecraft on the way to Mars, the Mars Odyssey spacecraft, and it lost its radiation instrument. It was knocked out by the levels of radiation. And that instrument was there to measure the radiation dose that astronauts might face. And had there been astronauts out in space between Earth and Mars at that time, they probably would have not survived. Because this was actually a solar system storm. The sun let off these clouds, and yes, there were effects at Earth, but these clouds filled large parts of the solar system, passing Earth, going to Mars. They were seen at Jupiter and Saturn by the Ulysses and Cassini spacecraft, and even the Voyager spacecraft out at the very edge of the solar system saw the whole heliosphere, the bubble of magnetic field surrounding the sun, puff out. Because just as Earth has its magnetosphere, its region of magnetic field that is separated from the solar wind, other planets like Jupiter and Saturn that have magnetic fields, and Mercury too, they have their own magnetospheres, their own bubbles, magnetic bubbles around them. And in fact, space is full of magnetic bubbles because our sun has a magnetic bubble around it, the heliosphere, and that is separating the solar system and the plasma and magnetic field of the sun from the magnetic field and the plasma of interstellar space and the interstellar magnetic field. There is a galactic magnetic field that is separate from the sun's magnetic field, and space then is really filled with bubbles inside of bubbles, and these bubbles being magnetic bubbles. It's, as I said, far, far from empty. And again, you know, when did we first start seeing that this could affect our technology? Well, it's when our technology allowed us to. Because the first great magnetic storm that had an effect on humans and human technology happened in 1859. And British astronomer Richard Carrington was observing sunspots when he observed actually a very rare white light flare. He saw a flare go off, and there was a huge magnetic storm that followed. Some people were already tempted to make the connection between the flares that Carrington had seen in the magnetic storm. Balfour Stewart, another British astronomer, wrote that there was potentially a connection with our luminary, by which he meant the sun. But that was not accepted until the 20th century, that there could be a real connection, because people didn't understand how that could happen. Now we have a pretty good idea how a lot of this stuff can happen. But there were real impacts. There were aurora reported in Havana, Cuba. Galveston saw aurora, Key West. There was a US Navy ship off the coast of Nicaragua that reported lights in the sky. And the telegraph, this was the key thing. The telegraph was then the internet of its day. And telegraph lines were strung by this time, you know, all the way out between Chicago and New York. And so you had long conductors, and that meant that they could collect up the electricity generated by this storm. And so telegraph operations in both Europe and North America were basically shut down for about a week. There was so much electric current flowing in the ground that outside of Boston, Massachusetts, some operators just stuck wires in the ground. And there was enough current running in the ground that they could make the telegraph work using that without batteries. Pretty remarkable. And all of this was collected up by a Yale physics professor, Elias Loomis, and published in a series of papers in the American Journal of Science. And so we worry about things like that now. What would happen if we had such a storm now? And there was a National Academies report in 2008 that said that we could have a pretty significant effect, $1 to $2 trillion versus of losses, and recovery time that in some cases could be quite long. If you blow out these really big transformers, we don't make too many of them each year, and they're hard to transport. So there could be places that could be without electricity for some time. Now, we experienced that last March with our winter storm, that many parts of DFW were without power for a while, and we all know how difficult that was. How, you know, what a tough event that was. Imagine a month in the summer in Dallas-Fort Worth without electricity because the power grid has been blown out by a major magnetic storm. So the power grid industry is well aware of this. They work to mitigate losses, but really what we need is to understand, to be able to predict space weather, because as my colleague Dan Baker showed in a paper in Space Weather in 2013, Space Weather is a journal actually, it reported on one of these big clouds that missed the Earth that could have been on the scale of the Carrington event. Fortunately for us, it sort of went off the other direction and did not hit Earth. So predicting space weather is a big deal, because if you can predict, then you can prepare. And if you can prepare, you can mitigate any losses. So just last fall, there was a bill passed and signed, the Promoting Research and Observations of Space Weather to Improve the Forecasting of Tomorrow, the ProSwift Act. This is just the latest in a series of bipartisan measures to enhance space weather prediction in the United States and to collaborate with other space agencies. But to improve prediction, you got to have better models. And NASA is establishing several modeling centers, heliophysics science centers, to create the enhanced models. And actually, UTA has one of them. I'll get to that in a moment. But our physics department actually has got very broad research areas, and very well funded by outside research dollars. And so there are many areas in which we work, but in particular in space physics, we have 4 faculty working in space physics now. Myself, Dr. Yue Deng, Dr. Dan Welling, and Dr. Rick Wilder, and we work on a variety of things like the coupling of the solar wind to the magnetosphere and very detailed work on ionospheric modeling. And we have one of these new centers. Now it's a phase 1 center, and NASA will cut back from all the phase 1s to a handful of phase 2s, but we are confident that we will end up with one of those phase 2 centers. And what we're studying is how do the models work when you actually have a north and south ionosphere, because actually the models right now only, they assume that they're identical, and they're not. And that's a big sort of blind spot for these models and their ability to accurately predict what's going to happen in our near-Earth space environment given a given input from the solar wind. So UTA has got a very strong space physics group. Of that $6.7 million, we're responsible for 20% of that, the space physics operation. And so we are really one of the leading groups in the country and actually in the world. And hopefully we will get the phase 2 center and really put UTA on in the front ranks of space physics research worldwide. So that is it for my presentation, and I guess I should stop sharing.
Ramon, thank you very much for your presentation. We really appreciate it. And Neela too, thank you for your presentation, and great way to start off our first Creative Escapes series. In the chat, again, I've mentioned if you've got any questions now for our presenters, we've got time for some question and answers. So if there's anything that you would like to pose to our presenters, or if you would like to make a comment about the presentation, feel free to put it into the chat now. Anything that you want to add to, Anne?
No, I just really appreciate everyone's kind comments in the chat from Ramon's talk, and I really appreciate our speakers. Did a fabulous job, Neela. Amazing. Love the photos that your students have shared, and Ramon, that's just amazing work that you all are doing. So we can stay on a little bit for any questions that you might have. Do you have anything? We have one.
So, yeah, go ahead, Ann.
So for would infinite mass be correct? So is that for Ramon?
For Ramon.
Yes.
Yeah, the answer is no. Actually, you can calculate the number of baryons in the universe, and baryons are the subatomic particles. Now, the ordinary matter, like baryons that we see, that's only 5% of what's in the universe. Then there's this other 20% that's dark matter that we have no idea what it is. And then the remaining 75% is dark energy, for which we have even less understanding of what it is. But one thing we are pretty sure of is that it is finite. So the universe is finite. Now, it's hard to imagine, how can it be finite if it has no edge? Because it doesn't. But imagine yourself as an ant on a beach ball. You can only see, immediately around you. And as far as you can tell, the horizon is just everywhere. And you can keep on walking along the surface of that beach ball and never, ever come to an edge. And yet the beach ball is finite. So we think the universe might be something like that, although we're not entirely sure.
Any other questions? Well, once again, we thank you. We thank you so much, our speakers. Thanks. We want to give you information to contact us on our programs. And here's the information for you if you would like to know more. We have Dr. Ramon and Dr. Neela's contact information here. And also the physics department website if you're interested in programs in physics. We also have the Center for Research on Teaching and Learning Excellence email and website if you would like more information on our programs here in CERTL. So please, please contact us. We are happy to hear from you at any time. And if you have questions later that you think of, please go ahead and send them on. Also, we have our next session on June 30th from 4 to 5 p.m. It will be Dr. Roger Gans, Marketing to People Who Don't Want to Be Marketed To from the Department of Communication, College of Arts, and Dr. Ritesh Saini, When Consumers Are Irrational, Department of Marketing, College of Business. So we look forward to seeing you then and hope you can attend. And thank you again, Dr. Neela and Dr. Ramon. Appreciate those wonderful presentations. Thank you so much.
You're welcome, Ann. There is actually another question, and I don't mind staying on a bit longer to answer questions.
For sure. Yeah.
There's a question, is space discrete? And I'm not entirely sure what the author of that question means, but to somebody like me, discrete means little pieces. And maybe. Again, it's the kind of thing that physicists like to argue about and speculate about. There's one very interesting idea out there called the simulation hypothesis, namely that any sufficiently advanced species will eventually, spread out through its entire galaxy and then convert all of the available matter into basically computer substrate and be able to do enormous calculations. And that one of the things that they might want to do is simulate their own universe to study where they came from. And that, in fact, we might be living in a simulation, kind of like a matrix, like the Matrix kind of thing. So believe it or not, there are physicists who are looking at, is this a possibility? And one of the things they're looking at is our universe really composed of a grid, which would indicate some kind of computational grid or computational space. And they're looking at that with very, very high energy cosmic rays to see if there's a sudden change in the spectrum at the very highest energies, because high energy means also small scale. They're inversely related. And at some tiny scale is space actually discrete, like a bunch of little points. So it's an interesting idea, and of course no idea is too crazy for some physicist somewhere to try to see if there's any merit to it.
That's great. Multiple universes, what about that, Ramon?
Multiple universes, again, you know, it sort of depends on whose particular theory of the month you're following. But yeah, there are plenty of ideas that lead inevitably to the idea of multiple universes.
Infinite universes.
Infinite universes, that at each point, the universe, at each instant, you know, and quantum mechanics tells us that things have certain probabilities of occurring, but that at each instance, every single probability that can occur, no matter how remote, does occur in some universe. And so that at every instant, you've got an infinite number of universes spawning off of the last one. And then at the very next instant, off of each of those, another infinite number of universes are spawned, etc. But there's no way to test that. So actually, if you cannot falsify a theory, if you cannot create a test to see if the theory actually holds, if it can explain a full range of observations, if you cannot construct an experiment that would show that a theory is false, then that theory is not a theory. It's just a belief that doesn't qualify as science.
At this moment.
Yeah, if you create a falsifiable experiment for a theory, then it is a theory. But if you cannot, if there's no way to test it, then it's not a theory. It's just a belief.
Yes. Right. Two separate things. Excellent.
Any other questions left?
Yep, we can. Happy to stay.
Well, I do need to get to another call, and should go do that. And since I don't see any new questions, but thanks everyone, especially those who stayed to the bitter end here, and thanks.
Wonderful.
For producing this.
Wonderful.
Yeah, thank you both.
Thank you so much.
Thank you.
Wonderful.
Thank you, everyone. Have a wonderful summer. Keep enjoying your surroundings and the skies.
Thank you.
Stay connected with your universe. Okay, bye-bye, everyone.
Bye, everyone.
Goodbye.
Thank you.